Okay, so we're looking at area and volume part 2 now. So we'll just move this down here, and I suppose the first place to begin is to talk about prisms. And prisms are basically objects with a uniform cross-section, and a rectangular solid prism looks like this, with a breadth, a length and a height, and the volume is the breadth by the length by the height, and the units are cubed, like meters cubed or centimeters cubed. Other prisms include triangular prisms, cylindrical prisms, and other shaped prisms, which have a cross-sectional area that's shaded and a length L. Each has a length L, and the volume of other prisms, or prisms in general, the volume is equal to the cross-sectional area times the length. So even for this up here, it would be this area here multiplied by the length. Okay, and the problems that you'll meet with this include something along the lines of this problem here, where we have a shape that has a cross-sectional area that's the shape of a trapezium, where we have 10 centimeters, 20 centimeters, and 40 centimeters, and the whole length of that trapezium-shaped prism is 30 centimeters long. So the way to find the volume of this shape would be to simply find the area of one end of the cross-sectional area using the formula for the trapezium, and that's equal to 600 centimeters squared, and to multiply that by L, which is the length of the prism. And so 30 times 600 gives us 18,000 centimeters cubed. So we just find the area of the face, and we multiply it by the length. In this chapter we also met with nets, and nets are two-dimensional representations of 3D shapes. So here is the net for the 3D shape that is a cube, like a dice. Here is the net for, here is the 3D shape, and here is its corresponding two-dimensional representation, its corresponding net. And the type of questions you'll meet with nets is that you might be given a net, you might be given a shape like this, and they'll ask you to draw it in 3 dimensions and or find its volume given other dimensions. Let's move on to cylinders and spheres. Here is our cylinder of height h and radius r. The volume of a cylinder is pi r squared h. Okay, and if we were to peel back the lid and the underside of the tin and roll out the tin itself, we would get a curved surface area here that's equal to 2 pi r h, and we have also the area of the circular lid as pi r squared, and the area here pi r squared. So the total surface area of the tin, if we took it apart and flattened it out, would be equal to 2 pi r all times h plus r. And we also met with the sphere. The sphere should be more of like a shape of a ball of radius r, and the volume of the sphere is given by 4/3 pi r cubed, and the surface area is 4 pi r squared. We also met with the hemisphere, which is the sphere cut in two, the volume of that being 2/3 pi r cubed, and the solid surface area of a hemisphere is 3 pi r squared. And you'll find all those formulas in your log tables. Okay, so what kind of questions do they ask when we think about cylinders and spheres? Well, there's the ones where you're just given the straightforward shape with its dimensions, and you just use the formula to find the volume. Sometimes you're given an actual numerical value for the volume and one known, and you find the other unknown. And a typical question that can come up in project maths is where we're finding the rise of water H in a cylinder after a ball has been dropped into it. And there's a standard approach to that type of problem. First thing to do is to calculate the volume of the ball, then you let that volume of the ball equal to pi r squared h, where this is the volume of the cylinder the ball has fallen into. So this is the radius of that cylinder and the height of that cylinder, and you simply find h. We'll look at an example or two of those in a second. And then the final type of question is I refer to as shapes in shapes, where shapes are, you find the volume of a sphere in a cylinder and so on. We'll look at an example in a second. Okay, a ball of radius 6 centimeters is dropped into a cylinder of water of radius 8. Find the rise in water H. So, remember our steps. The volume of the ball is 4 over 3 pi r cubed. That's 4 over 3 pi times 6 cubed is 288 pi. And it's okay to leave that as something pi just for the moment. Then we let that volume, 288 pi, equal pi r squared H. Remember, this is for the cylinder, okay, of radius 8. Okay, so 288 pi equals pi by 8 squared H. 288 pi is pi 64 H. So H must be 288 pi divided by 64 pi. Now they can cancel, or you can multiply 288 times pi and divide them all by 64 times pi. Either way, you'll get the H, the rise, equal to 4.5 centimeters. Let's look at a second example. A golf ball has diameter 4 centimeters. It is dropped to a cylindrical hole of diameter 10 and height 12 centimeters. It is half full of water. How much does the water rise H? Okay. Well, first thing again, find the volume of the ball. 4 over 3 pi r. If that's 4, r equals 2. 2 cubed, so it's 10.6 pi. Then we let that 10.6 pi equal pi r squared H, where we're referring to the radius of the cylinder. The diameter is 10, so the radius is equal to 5. So we have 10.6 pi equals pi by 25 H. So therefore H must be equal to 10.6 pi over 25 pi. They'll cancel. H is equal to 0.424 centimeters. And another, sorry, this is the type 4 type problems that appear with spheres and cylinders. Shapes and shapes, I call these ones. So a piece of art is carved from stone rectangle with a square base. It has a height of 24 centimeters. It consists of 2 cubes and 2 spheres. The diameter of the spheres is equal to the sides of the cubes, and the cubes are identical and the spheres are identical. Okay, so this is what it looks like here. We have a cube, a sphere, a cube, and a sphere, and it's all out this original piece, rectangular piece of wood or stone. Sorry. Okay. So find the length. First part is find the length of one side of the cube. Well, you know, if the cubes and the spheres have the same as the cube, if it has the same length as the sphere, and it is a cube, all the sides of the cube are the same. So if this is the same as the diameter of the sphere, this must be the same length for the cube, and that's the same length. And there's the same, and that's the same, and that's the same. So really, the 24, to find the length of one side of the cube, must be 24 divided by 4, 6 centimeters. Okay, and then we're asked to find the volume of the piece of art itself. So that's a cube plus a sphere plus a sphere. So the cube, if one side is 6, the other sides must be 6 as well, because it's a cube. So the volume of the cubes is 6 by 6 by 6, and the volume of the spheres are 4 over 3 pi r cubed. And if this is 6, then the radius r must be equal to 3. So we plug that all into the formula, and we get the volume of the ornament as 658.2 centimeters cubed. And finally, we're asked to find the percentage of the stone chipped off the stone block, the rectangular block, the bits of stone that hit the floor, basically. So the chipped stone amount, the stone that fell off onto the floor, is equal to the original volume of the rectangle minus the volume of the ornament. So that's 864, because our volume of the original rectangle must be 24 by 6 by 6. Okay, because we met with that before when we got the volume of a rectangle. It's LBH. Okay, so 864 minus the ornament itself means that 205.8 centimeters cubes of stone hit the floor. So the percentage waste is that amount divided by the original volume of the rectangle times 100. So 24% of the stone hit the floor and 76% remains as ornament.